Hi everyone, and thanks for joining me for our first tutorial for SPPH 500. My name is Mary Claire. In this tutorial, I'm just going to review simple linear regression and conclude by examining a dataset in R. So why are we interested in regression? And more specifically, multiple linear regression. So let's turn to an example to discuss why we're interested. You are interested in examining what approach is best for the treatment of chronic back pain. You have data from 44 physicians who are treating 1,071 patients for back pain over 2 years. Each physician is categorized as providing low, medium, and highly aggressive treatment for back pain. Possible outcomes of interest include patient-reported outcomes, cost of treatment, pain, resumption of regular activity, number of physician visits, etc. You also have information on patients' age, gender, marital status, and other comorbidities. So why can't we simply compare the means between the low, medium, and high treatment groups? The reason is that the three groups, low, medium, and high, might differ in other ways aside from treatment type that affect the outcomes that you're interested in. So for example, groups could be older, differ by gender, or have other health concerns that impact your outcome. This would bias your results if you're trying to estimate the impact of the treatment on your outcomes of interest. Using multivariable regression allows you to control for variables that may confound the association between treatment and your outcome of interest, in order to minimize the bias of your results that estimate this relationship. So you could have a multivariable regression model where you adjust for age, gender, and other comorbidities, for example. And by adjust, I mean holding constant or removing their effect to get a less biased estimate of the association between treatment group and your outcome. So this is something we went over near the end of SPPH 400. While we mostly talked about linear regression in 400, which is used to model continuous outcome variables, regression can also be extended to examine other types of outcome variables. Logistic regression is used with binary outcome variables. For example, do you have the disease or condition? Yes versus no. Poisson is used to model counts or rates as the outcome. The distributions for Poisson are often skewed to the right, which is one of the main reasons why we can't simply use linear regression in this case. And survival analysis is used to model time to an event occurring. In this course, we're going to learn about each of these different types of regression models. The outcomes differ, but you'll see that the core concepts for these are largely the same. The course starts with linear regression, and then most of the concepts you'll be able to apply to the other types of regression models, which are known as generalized linear models. So let's return to our example. We could use each of the 4 types of regression models to examine outcomes of interest here. For example, we could use linear regression if our outcome was cost of treatment. Logistic regression could be used if the outcome was resumption of regular activity, yes versus no. Survival analysis could be used to model time to resumption of activity, and Poisson regression could be used with an outcome of number of physician visits, which is likely to be skewed to the right. So before you conduct any sort of multivariable analysis, you should always do some initial data exploration. First, it's a good idea to look at all the variables that you're interested in individually, whether through descriptive statistics or univariate plots. This will help you to identify extreme values or outliers in your dataset that you may need to address in some way. And this will also help you to look for data entry errors. So for example, you might have a variable that ranges from 1 to 5 or is yes versus no, and have a value entered that isn't even a possible response option. This will also help you to get an idea of the shape or distribution of each individual variable, which can be important in helping you determine whether or not your data meet the assumptions for the analysis that you want to do. You should also examine the bivariable relationships between your variables. You should first look at the bivariable association between your outcome and all explanatory variables that you're interested in before proceeding to multivariable analysis. And then you should examine the relationship between the primary explanatory variable and your other explanatory variables. So this can help you identify confounding, collinearity, and other problems that may affect your analyses, which we'll discuss in greater detail as we progress in the course. So in R, it's important to first check each of the variables to check for any errors. You should also make sure that your variables are correctly coded and that R is recognizing these correctly as continuous or categorical. So you can use the class function in R to find out how the variable is recognized by R. Something to note is that R will always treat variables as continuous or integers until you tell it that these are categorical. If your variable is wrongly coded as continuous when it should be categorical, you can change it using the factor command in R. Once you have the variables classified correctly, you should then look at numerical summaries. So for example, statistics like the mean, median, standard deviation, range, frequencies, percentages, and cumulative percentages. You can also use graphical summaries like histograms, box plots, and QQ plots. Once you're finished checking out each of these variables independently, you can move on to bivariable descriptions. For example, you can use plots like scatter plots and side-by-side box plots, or you can use hypothesis tests like a t-test, chi-squared test, ANOVA, Pearson's correlation, or simple linear regression. You can do this to examine the relationships between your explanatory and outcome variable, or the relationship between your explanatory variables. We went over this in detail in 400, so I'm not going to discuss this, but this is just a reminder of how you can display univariate or bivariate data depending on whether your variables are quantitative or qualitative. So now let's turn to an overview of simple linear regression. This method is used when you want to model the linear relationship between a single quantitative explanatory variable and a single quantitative outcome variable, although it can also be used to estimate the relationship between a qualitative explanatory variable and a quantitative outcome. The null hypothesis is that beta 1, or the slope for the relationship between x and y, equals 0. The alternative hypothesis is that the slope does not equal 0. You can calculate the confidence interval for the slope using code in R. With simple linear regression, you're using knowledge of your explanatory variable to explain or predict your outcome variable. With simple linear regression, we fit a line to model the linear relationship between x and y. So this is the formula for the fitted regression line. The y hat is the predicted value of y for a given value of x. In other words, it's the mean y value for a given value of x. So the predicted mean value of y for a given x is the sum of the intercept plus the slope times the given x value. Here's a visual representation of the regression line. Beta 0 is the estimate of the intercept, or the mean value of y when x equals 0. Beta 1 is the estimate of the slope. It is the average change in y for every 1 unit increase in x. It's also important to note here that the regression line must pass through the mean point, the point whose coordinates are the mean of x and the mean of y. When we fit a regression line, there is almost always some error associated with this line. The error is the difference between the observed y values and the predicted y values along the regression line. The most common method to fit a regression line is the method of least squares, which is also known as the maximum likelihood method. So this method finds the line that minimizes the variation or error around the regression line. In other words, it finds the best line that minimizes the sum of the squared difference between each actual observed y value and the predicted y value. We want to minimize the error associated with our model because the smaller the error, the better our model will be at making predictions. The error or residual associated with the regression line represents what is not explained by the model, the difference between the observed data points, so the actual data points, and the expected or predicted data points. The mathematical details of regression are not that important for this course, so you won't ever have to calculate the error or the slope or anything like that by hand. The most important things are to understand the main concepts and how to interpret the output produced. This plot shows us an example of a fitted regression line through a scatter plot of observations. Each circle shows the observed y value. The blue line is our predicted value of y for a given x. The red lines show the error or residual, the differences between the observed and predicted values. The variance of y given x is just the variation of observations around the regression line. It is the sum of the squared difference between each observed y value and the predicted y value. The standard deviation of y given x is the standard deviation of observations around the regression line. It answers the question, on average, how far do observations deviate from the regression line? So as I mentioned, the method of least squares, or maximum likelihood method, is the method of finding the line that minimizes the variation, or error, around the regression line. This method chooses the line that minimizes the variation of observations around the regression line, the sum of squared errors, because we want to minimize the error associated with our model. So if we took all the red lines shown on the previous slide, squared those distances, and then summed them up, the best line would be the line for which that value is the smallest. Also, as I mentioned, the error associated with our regression represents what is not explained by the model. So this may be due to residual confounding, so some other important explanatory variable could be missing, or it could be due to the measurement of included variables, among other things. So now we'll go over how to interpret simple linear regression output. The R code for conducting simple linear regression in R is shown at the top. In the red box, the intercept is shown to be 103.31. This tells us that the mean value of y is 103.3 when x equals 0. The intercept is often a meaningless statistic on its own, because often it doesn't make sense for a variable to take on a value of 0. So we can center the explanatory variable to give the intercept a more meaningful interpretation. We talked about this in 400, but this means that the mean x value will be subtracted from each individual x value. When x is centered, the intercept tells us the mean value of y for the average level of x. Below the intercept in the red box is the slope associated with the variable x. This tells us the average change in y for each 1 unit increase in x. For example, for each 1 unit increase in x, we see y increase by an average of 1.67 units. Remember that it's important to always relate your interpretations to the context of the example, including by referring to the specific variables and the groups compared, as well as the units of your variables. To the right of the intercept and the slope are the standard errors associated with these statistics. The standard error of the slope tells us how close our estimate of the slope is to the true population slope. Recall that the slope in our output is our best estimate of the true population slope for the relationship between x and y. And so the standard error tells us, on average, how far will our estimate of the slope move or vary from the true population slope. We are usually most interested in the standard error of the slope because our null and alternative hypotheses are focused on the slope. If we wanted to make a confidence interval for the slope, this is calculated as approximately plus or minus 2 times the standard error. The t-value shown to the right of the standard error measures whether or not the coefficient for this variable is meaningful for the model. Researchers usually don't interpret this value by itself, and so you probably won't use this value, but it's used to calculate the p-value associated with the slope. This p-value tells you whether or not you should reject or fail to reject the null hypothesis, that the slope equals 0. In this example, we can see that the p-value associated with the slope is 0.003. Since this is less than the significance level of 0.05, we reject the null hypothesis that the slope equals 0 and conclude that we have evidence to believe that the slope is not equal to 0. As we talked about, the residuals or error are the difference between the actual values of a variable you're predicting and the predicted values from your regression model. So you can plot the residuals as a way to check the assumptions, which we'll discuss shortly. The residual standard error is the standard deviation of your residuals. It tells us how far individual observations move from the regression line on average, or how much observed values vary from the predicted values on average. It's basically the standard deviation of the error terms. So it can be helpful to think of this as the average error. The F statistic tests the null hypothesis that all of the betas for the covariates or explanatory variables in our model are equal to 0. In this example, we only have one covariate, or x variable. Since our p-value is less than 0.05, we reject the null hypothesis and conclude that we have evidence to believe that the covariate x has predictive power in our linear model. The F statistic basically tells us if our model is better than nothing, so it's not really all that informative. The output also shows you the R-squared. This is a metric for evaluating the goodness of fit of your model. It tells us the proportion of the variability in y that is explained by your explanatory variables. It is calculated as the variability in y values that is explained by the x's, divided by the total amount of variation in the y values. The R-squared ranges from 0 to 1. The closer it is to 1, the better our model is at making predictions. So if the R-squared equals 0.75, this tells us that 75% of the variability in y is explained by the x variable. In multiple linear regression, the R-squared tells us the proportion of the variation in y that is explained by the explanatory variables in the model. The R-squared is also known as the coefficient of determination. And the R-squared is calculated by dividing the sum of the squares of the model by the sum of squared total. You'll recall that the sum of squared model is the variability in the y values that is explained by x. And the sum of squared total is the total amount of variation in the y values. So the R-squared is calculated by dividing the sum of squared model by the sum of squared total. So now let's turn to the assumptions of simple linear regression, which also apply to multiple linear regression. The first assumption is linearity, which means that the association between the two variables is linear, or the mean of y for a given value of x is a straight linear function. Independence is the second assumption, and this means that the errors or residuals are independent. Normality is the third assumption. So for each value of x, the values of y are normally distributed, which also means that the errors are normally distributed. And the final assumption is equal variance, or homoscedasticity. This means that the error variance is constant. So the variation around the regression line is approximately the same at each point along the line. We use a diagnostic or residual plot to check the linearity and equal variance assumptions. Independence is checked through knowledge of study design, and normality is assessed by using a QQ plot. So let's review how to check linearity, normality, and equal variance using residual and QQ plots. We check linearity using a residuals versus fitted plot. If there's no pattern to the residuals plotted against the fitted values, you can assume that the linearity assumption is met. When you look at a residual plot in R, you're looking for no pattern to the residuals versus fitted values and a smooth red line through the residuals plot. So we can assume that the linearity assumption is approximately met in the plot on the left and the plot on the bottom because there's no obvious patterns to the points and the line is pretty straight through the plots. But there is curvature to the points in the plot in the middle and on the right, so the linearity assumption is violated in these instances. Here are another couple of examples. The plot on the left looks to be approximately linear, but there's curvature to the points to the plot on the right, so the linearity assumption is violated here. You'll recall that scatter plots can also be used to check linearity with simple linear regression models. So if you used a scatter plot to examine the relationship between x and y for these two examples, you would come to the same conclusions. But the problem is that scatter plots cannot be used to assess linearity with multiple linear regression, where you have two or more explanatory variables. But you can use the residuals plots to check linearity with multiple linear regression. So it's probably best to just get in the habit of checking the linearity assumption with residuals plots. We can also check for homoscedasticity with the residuals versus fitted plot. If there's no pattern to the residuals versus fitted values and the cloud of points is constant, you can assume that the homoscedasticity assumption is met. When the cloud of points is not constant, this is known as heteroscedasticity. The plot on the top shows the most common way that heteroscedasticity will arise in a dataset, with a cone shape surrounding the line. On the other hand, the plot on the bottom and the right are fairly constant, or homoscedastic, because the cloud of points is fairly constant around the line. Returning to our previous examples, we can see that the plot on the left is approximately homoscedastic, as there is no pattern to the residuals versus fitted values. With the plot on the right, it's hard to assess the homoscedasticity assumption because the linearity assumption is violated. But there appears to be a pattern to the points, so the homoscedasticity assumption would also be violated in this instance. If you use some sort of transformation to try to address the linearity issue, like logging or taking the square root of the x variable, you could then produce a new residuals plot to see if the data meet the homoscedasticity assumption. We can assess normality with what's known as a QQ plot. If the line is a straight diagonal line, you can assume that the normality assumption is met. So we can see that the plot on the top left and the plot on the right meet the normality assumption, but the other two plots on the middle and the bottom left do not. The middle plot is skewed to the right and the bottom plot is skewed to the left. So a curved line appears in the QQ plots because the normality assumption is violated. Here are another couple of examples. The plot on the left is approximately normal, but the plot on the right isn't because there's curvature to the line. So let's walk through an example in R using the FEV data that most of you should be familiar with since we work with this in 400. The R script and the dataset for this analysis are also posted on Connect. The first step is to read in the data into R. You can attach the data if you like, but I prefer not to most of the time because you can accidentally make changes to your dataset that can be difficult to correct. So we import the data into R and then ask R for a summary of the data. This gives us summary statistics for each of the variables in our dataset. So let's take a look at what this looks like. So if we look at a summary of our variables, we can see a problem. The gender, smoke, and age category variables should be categorical, but R is recognizing these as continuous variables. We can also see this if we use the class function, which tells us how our variables are recognized in R. So all three of these variables are being read by R as integer or continuous variables. But we can correct this issue by using the asFactor command in R. We can also tell R the names of the different categories for these variables. So for example, women and men for the gender variable. And the code for this isn't shown here, but you can check this out in the R script on Connect. If we rerun the summary command, we can see that R now tells us the number of individuals in each category of the categorical variables, rather than provide descriptive statistics like the mean, median, and interquartile range, which are only appropriate for describing continuous variables. So these summaries for our variables provide important information about the distributions and allow us to identify any potential errors. But we could also use univariate plots to look at the distributions and see if there are outliers and other things. So once we've looked at the univariate statistics, the next thing we'll want to do is check out our bivariate relationships. The R script shows how to produce these plots, including how to pretty these up by including labels and colors. For example, we could use box plots to examine the relationship between FEV and smoking status, and FEV and categorical age. So here we can see that the FEV of smokers appears to be higher than non-smokers, and that FEV tends to increase with age. We could also look at scatter plots to examine the bivariate associations between our outcome of interest, FEV, with age and height. So based on these bivariate analyses, we have a good idea of the relationship between our variables. It appears that smokers might have higher FEV than non-smokers, but smokers also tend to be older than non-smokers. And this is important because age is also positively associated with FEV. So this may actually be driving the bivariate relationship we see between smoking and increased FEV. In other words, age may be a confounder. We can also use simple linear regression to examine the bivariate relationship between FEV and smoking status. Our outcome of interest is FEV, which is a continuous variable, and our explanatory variable of interest is smoking status, which is a categorical variable. It's important to think this through to make sure simple linear regression is appropriate, or if we should be using another form of analysis like logistic or Poisson regression. But because our outcome is continuous, linear regression is appropriate here. So we fit a simple linear regression model in R and get a summary of the model. The intercept tells us that the average FEV value for non-smokers is 2.556 liters. The slope for the smoke variable tells us that smokers have an FEV that's an average of 0.71 liters higher than non-smokers. The p-value associated with this slope is less than 0.05, so we can reject the null hypothesis that there's no difference in FEV between smokers and non-smokers and have evidence to suggest that the FEV of these two groups are different. We can also fit a model to examine the relationship between FEV and categorical age. This is where it becomes important that age cat was coded correctly as a categorical variable. Let's take a look at what happens if it's coded incorrectly as a continuous variable. So our age cat variable has 4 levels or groups. So what we should have is 3 slopes in our output for the 3 groups in comparison to a reference age category. But we only see 1 slope in our output here. So what assumption is R making when age cat is treated as a continuous variable? It's assuming that increases in FEV are proportional with increases in age category. So the increase in FEV from age category A to B is the same as the increase in FEV from age category B to C and C to D. Let's run our model again, but this time with age cat treated correctly as a categorical variable. We can see that we have 3 slopes rather than 1, which is what we want to see. The reference group is age category 1, so each of the slopes represent the difference between that age category and age category 1. So for example, those in age category 3 have an FEV that's an average of 1.99 liters higher than those in age category 1. Those in age category 4 have an FEV that's an average of 2.58 liters higher than those in age category 1. If we look at the slopes, we can see that the increase in FEV is not proportional with each increase in age category. If it was, we would see, for example, that the slope for age category 2 versus 1 would be 0.9, and then the slope for age category 3 versus 1 would be 1.8, or 0.9 times 2, and the slope for age category 4 would be 2.7, or 0.9 times 3. But what we see here is that there's a greater increase in FEV between age category 2 and 3, so more than a liter difference when compared to category 1, whereas there's a smaller difference in FEV between age category 3 and 4, about a 0.6 of a liter difference when compared to age category 1. So FEV does not increase proportionally with increases in age category. We could also rerun our model, but with a continuous age variable. Here we see that we have a single coefficient for age. The slope tells us that for each 1 year increase in age, FEV increases by an average of 0.22 liters. When we use this continuous age variable, we're assuming that the increase in FEV is the same or proportional with each increase year in age. So the difference in FEV between someone age 17 versus someone age 16 is the same as the difference between someone age 8 versus someone age 7. So which age variable do you think is more appropriate to use in our model? Based on the available information from our analysis so far, it seems like it would be a better idea to use categorical age, because we don't see FEV increase proportionally with increases in age. Instead, there seems to be a positive linear association between age and FEV up to age category C, or about age 12, but then this levels off, and there's not much difference between those in the older ages of our sample. So there actually appears to be a non-linear relationship between age and FEV. So using the categorical age variable in our model will give us a more accurate representation of the relationship between age and FEV. In the next tutorial, we're going to review the goals of regression modeling, introduce multiple linear regression, and discuss how to compare models.